So I thought it'd be interesting to take a look at some of the different carbonyls, particularly here we're just looking at some first row transition metal carbonyls. Carbonyls are known to form a wide variety of different structures because, as you'll see, they can form bridging ligands. And so let's go through this a little bit here. So, we predict that those with 18 electrons are going to be the most stable. So if we look at something like vanadium hexacarbonyl, well, that has 17 electrons, and carbonyl or carbon monoxide, it's called carbonyl when it's in a transition metal complex. That's a 2-electron ligand. It's donating through a lone pair. And vanadium, you can see here, is a 5-valence electron. So that's the closest it can get without getting 19 electrons. You don't want to make 19 electrons. That's putting electron into the antibonding orbital if you don't have to. So yeah, this is right 5 for vanadium plus 6 times 2. That's how you get 17. And so the anion, though, is very, very stable because that's going to have 18 electrons, right? That's going to be negatively charged. Chromium, that's moving over 1 on the periodic table, so that's going to be in group 6. Chromium hexacarbonyl is a neutral complex, is going to be stable because it has 18 electrons. You can see iron pentacarbonyl. Right now, you only want 5 carbonyls there, so it wants to be pentacoordinate because iron is in group 10. If you look on the periodic table, and so there, sorry, group 8. Okay, nickel is in group 10. So yeah, this is going to be 8 plus 5 times 2. Okay, so that gets you 18. And this is going to be 10 plus 4 times 2, nickel being in group 2. So it kind of helps you explain the different coordination geometries of these simple carbonyls. What about this manganese one? This looks pretty interesting. How does that work? Well, if you have manganese as just a monomer, not a dimer like this, manganese hexacarbonyl, that would have 19 electrons. So that's not going to happen. But what it can do instead is form a 6-coordinate complex, right? 6 coordinates are very common geometry, so it's stable from that standpoint. That also has 18 electrons. So let's just see how the electron counting would work in that case. So we have something like this, right? We have all these carbonyls. Each manganese is going to have 5 different carbonyls, right? And so each of these carbonyls, just like normally, is going to donate 2 electrons. And so if you look at the structure, there's one thing you can do quite easily is you can just notice that this is actually symmetric, right? And so it's symmetric through this double bond, right? And so what we can do is just kind of look at 1/2 of the structure at a time. And so again, manganese is in group 7, okay? So that has 7 valence electrons. And then we have 2, 2, 2, 2, 2. So we're at 17, right? 5 2s, 10, plus 7 is 17. And where we're going to get to 18 for the extra electron, sorry, this is why it's not manganese hexacarbonyl. I'm not sure if I said that right. Manganese hexacarbonyl is going to have 19 electrons. But this has 18 electrons because right now we have 17 electrons, but then we're sharing, right? This is 2 electrons in a bond there. We're sharing an electron with another manganese atom. So in total, we're going to get 18 electrons for this manganese atom, and this manganese atom is exactly the same, also has 18 electrons. So by dimerizing like this, these metal carbonyls can become stable and achieve the 18 electron rule. So you can use the 18 electron rule to, rationalize the structure of a lot of these complicated carbonyls. So yeah, basically, right, remember there's 2 electrons in a bond formally, usually. And so because you're sharing 2, each manganese gets an extra 1, basically, from the other one. All right, so there's many exceptions. We went over the 16 electron rule for square planar complexes I mentioned on the last video. There's a lot of other exceptions. This can be due to different d orbital splitting patterns and different geometries, or due to steric effects that could block like a lot of ligands from coming in, which may have you having less than the appropriate number of ligands. A lot of time, appropriate number of ligands to get you to the 18 electron rule. A lot of times in the early transition metal complexes like yttrium, zirconium, titanium, scandium, even vanadium and niobium, those don't have a lot of electrons to begin with. So it's hard for them to get to the 18 electron rule, especially if you don't have like highly ligands with a lot of electrons to donate. So a lot of times those will violate the electron rule, and sometimes quite badly. They'll only have, stable complexes are known that only have 10 or 12 valence electrons. All right, and that's just because, you can't get all of these ligands around the center and have the bonding all work out. And so what do? Well, you violate the 18 electron rule, and that's okay in some circumstances. All right, so some practice problems. Explain why cobalt, carbonyl, and tetracarbonyl and pentacarbonyl aren't stable. Okay, well, if we look at cobalt, right, we're at 9 valence electrons, and then we know that this is a carbonyl is a 2 electron ligand. So that's going to be 9 plus 4 times 2 is going to be 17. That's not the 18 electron rule. And this one is going to be 9 plus 5 times 2. That's going to be 19 valence electrons. So, not ideal because it's 18 electrons. 2 dimers below in solution are stable. Explain. All right, so if they're stable, we're probably thinking there's going to be the 18 electron rule. Let's start with this one on the right. It's looking a little more simple than this one on the left, right? So this is very similar to the manganese example. We have 2, 2, 2, 2. I noticed that this structure is symmetric across the middle, so I'm only going to really look at one half, and then whatever is on one half, I can apply to the other half. Cobalt has 9, and so this is at 17 valence electrons. We're sharing 2 electrons here, so cobalt's going to get an extra 1. Each cobalt's going to get an extra 1, so that gives us 18 valence electrons. It's following the 18 electron rule. Same thing with this 18. That explains why that structure is stable. But interestingly, these 2 dimers interconvert, so this structure must also follow the 18 electron rule. Let's see. Again, this is symmetric, okay, through the center here. So what we're going to do is look at this. So we know there's a 2 electron donor for carbonyl. We know cobalt has 9 electrons. Yeah, I know it's confusing because cobalt and CO look very similar, right? But the lowercase o is what its cobalt is, okay? And CO here, that's a 2 electron ligand, but it's being shared. This is called a bridging ligand. And so this is only worth 1 and this is only worth 1 because those 2 electrons are being shared. This is worth 1 and this is worth 1. But then we also have a metal-metal bond. And so each of the cobalts get an extra 1. So if we look on this side right here, what do we have? We have 9 plus 1 is 10, 11, 12, 14, 16, 18, 18 valence electrons for cobalt. If we did the logic on this side, it would be exactly the same. All right, rationalize the following reduction. Well, this is the structure that we just looked at. So, okay, fine, this is stable because of the 18 electrons. Why would adding 2 electrons to this cause it to turn into a monomer, cause it to monomerize? Well, we can look at this, right? And this structure is pretty simple. Cobalt has 9, 2, 2, 2, 2 for each carbonyl, 1 more for the charge. If you add all that up together, 9 plus 2 plus 2 plus 2 plus 2 plus 1, that equals 18. All right, so a lot of cool information that you can get and predict sort of these complicated structures, right? Just using the 18 electron rule.